Hello, welcome back to Math 155. This is a recording for problem class 29. Unfortunately, I'm not able to be there today. Have a go at some of these problems before I show you the solutions. So pause the video after I've introduced them and then check your answers against what I give you. Okay, so first of all, we've got a food web. This is the same basic food web that we looked at the other day. And here we're just going to try to first of all look at what are the unique predator-dominant species, then the trophic status dominant species, and then finally draw the competition graph. So first of all, a unique predator-dominant species is a species which is the only predator for a particular prey species. So how do we work this out? First of all, we need to find species with out degree 1. So in this food web here, let's find the species with out degree 1. Let's see, H, I, F, and C. So these 4 species, they have out degree 1 because they only have 1 arrow going out of them, which means that there is only 1 species that feeds on them. So to find the unique predator-dominant species, we just look at the species that are on the ends of these arrows. So in this case, we have J, K, I, and F. These are our unique predator-dominant species. So note here that F is a herbivore, but for our definition here of unique predator-dominant species, we're going to include this herbivore here as it is uniquely dominant. So the predator part of this is sort of slightly less important. The fact that it's a unique dominant species is the more important part here. Okay, let's move on to part B, trophic status dominant species. So a species is trophic status dominant if it has trophic status greater than the number of non-primary producers in the food web. So in this case, let's see how many species there are that are non-primary producers. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 non-primary producers in this food web. So we need to identify species that have trophic status greater than 8. So we look at J, T of J, its trophic status is equal to 11, which is greater than 8. So J is trophic status dominant. And K is trophic status 14, also greater than 8. So K is also trophic status dominant. The next highest thing we have here is species I, which has trophic status 8, but this is not greater than 8. So I is not a trophic status dominant species. Okay, part C, we're asked to draw the competition graph. Now, competition graphs tend to be somewhere that students fall down with this. So let's just go through this in detail and make sure this is quite clear. A competition graph is telling us some of the information that we have in our food web. And it's focusing on when species are competing with each other for food. So what does it mean for a species to be competing for food? Well, we need to look for all species that have out degree of 2 or more. Okay, so let's identify species that have out degree of 2 or more. So let's see, A has 3 arrows coming out of it, B has 3 arrows, C only has 1 arrow coming out of it. So we're not going to be having any competition between species for food source C. D has 2 arrows, E has 2 arrows, F only has 1 arrow coming out of it. G has no arrows, neither does J or K. H has no arrows coming out of it. Only has 1 arrow coming out of it, and I only has 1 arrow coming out of it. So we're only going to be getting competition for species A, B, D, and E. So what does our competition graph look like? Well, what we need to do then is we need to look at which species eat A, B, D, and E. So which species eat A, B, D, and E? Well, let's start with competition for species A. We can see, I'm going to circle these here. So species D, E, and F all compete for species A. So that means in our competition graph, we want there to be, this is D, E, and F. We want there to be edges between them because that's indicating competition between these species. So it's competition between species D, E, and F for species A. So in our competition graph, we draw links between them. Okay, now we just move through the others. So how about species B? Species B, we have competition between species D, which we've already got a circle around, and species F. Again, we've already got a circle around that. So we've already got a line in this. We don't need to draw another line in here between D and F because we already know they're competing for A. We also have competition with species H. So that means in my competition graph, when I add H on, there needs to be a link between D and H and F and H. Okay, so that's competition for species A and B dealt with. Now we need to think about competition for species D. So which species eat D? Well, that's G and H. So that means that there needs to be a line between G and H in our competition graph. And finally, which species eat E, H, and I? So I here, there's something there. Now the last thing here is that we need to have all of our other species. They are disconnected from the competition graph. These species do not compete with any other species for food. So that's A, B, C, J, and K. I've got myself an extra vertex there that I don't need. So that is my competition graph. Note that it doesn't matter how I arrange these nodes and edges on the page. What matters is the actual links that we have. Okay, for this problem, we want to consider a food web, and we're going to assume that species can survive on 50% of their normal diet. So this is a weighted food web because we have these weights here. For example, 100% of the diet for prairie dogs is grasses and berries, but for lynx, 10% is going to be black-footed ferret, and 90% is going to be snowshoe hare. So what we're going to ask here is describe the effect on the food web from the removal of snowshoe hares. And we're going to stick to things that we know will definitely happen. Okay, so let's think about what happens if we get rid of snowshoe hares. That means that this edge is going to be removed, and this edge is also going to be removed. So what does that mean? That means that lynx are going to lose 90% of their diet. So lynx are going to die off. They're going to go extinct as they lose 90% of their diet. Now, if lynx are now dead, that means this link here and this link here are also gone. So that means that grizzly bears are going to lose 30% of their diet. But we're told that a species can survive on 50% of its normal diet. So they survive. As I discussed in the problem class on Monday, there are lots of other potential things that we could say might happen. For example, there might be more black-footed ferrets around because the lynx aren't feeding on them, which means that maybe the grizzlies can eat more black-footed ferrets, so they might be able to adjust their diet accordingly. But we don't know these things for sure. We can't really understand what's going to go on unless we have a full population dynamic framework for this food web. But what you can say for certain is that if we remove the snowshoe hares, lynx will lose 90% of their diet. Therefore, they're going to go extinct. Grizzly bears will then lose 30% of their diet because lynx have gone extinct, but they're able to survive. Okay, so moving on from food webs, the pre-lecture also talked about compartment models. And we have met compartment models before, earlier in the semester, when we were doing things like looking at movement between juvenile and adult classes or between different locations. And so we would have matrix models of the form, say, xn plus 1, where x is a state vector, is equal to some matrix A times by state vector in time step or year or generation n. And we can encode these matrices here in graph form and vice versa. So we can go back and forth between these graphical representations as directed graphs and these matrix models. So that means that we can encode this information here in a matrix A for this digraph. So how do we do that? Well, we've got 4 different compartments here. And I'm going to put them in this order A, B, C, D, A, B, C, D. Now, these bits I've just put on here for illustration. You don't need to include these here. These are just to indicate what's going on. So just think of them as labels at the moment to help clarify. Ordinarily, you wouldn't put these on there. The other thing is that the order of my rows and my columns, they don't matter for the presentation of this digraph. We can switch around the rows and columns as long as we're consistent. So I could put DCBA, DCBA on my rows and columns. Okay, so I want to encode this information here. How do I do that? Well, let's first of all look at compartment A. So a link from A to A, if there was a link like this, then this would go, or I'm putting a 0 here. Okay, there's a 0 there because there is no edge linking A to itself. In fact, there's no edge linking any of these nodes to themselves, any of these different classes. So we know that on this main diagonal, we're going to have zeros. Then now we need to look at what edges are coming out of A. So we have this edge here from A to C, this edge here from A to B. So from A to B on this second row, we're going to have this weight of 1. So this is this one here. And then from A to C, we have weight 5. There is no A to D. So that is 0. Now we do the same for node B. There's only one arrow coming out of B, which goes to C. So there's no arrows to A, 2 going to C, and 0 to D. From C, we have this arrow going to A of weight 6, and this one going to D of weight 3. So we have 6 from C to A, 0 from C to B, and 3 from C to D. And then finally, we just have one arrow coming out of D, weight 4 going to A. So we have 4, nothing to B, nothing to C. And that is the matrix that corresponds to this digraph. Okay, so let's think about going in the opposite direction now. So here we've got a matrix and we want to construct a digraph that corresponds to this matrix. I'm going to first of all give each of these rows and columns labels. So I'm going to call this first row, second row, and third row. First and second and third column to be V1, V2, V3, and do the same for my rows. And then I need to construct my graph, a directed graph, encoding this information. So what can we do? Let's start off with this first column here. So this is describing everything going from V1 into something else. So we have V1 going to V1 is 0.8. We have V1 going to V2, 0, so there is no V1 to V2 arrow. And there's a V1 to V3 arrow here, weight 1.2. In the second column, exactly the same. This is everything coming out of V2. So V2 to V2, we have weight 2. And V2 to V1, we have 1.7. There's no V2 to V3, that has weight 0. Finally, everything from V3 to the other vertices. There's only one here that goes from V3 to V2, and that has weight 3.1. So this is the graph that corresponds to the matrix above. So we use these types of compartment models for various population models, as well as for things like drug models. So understanding how, say, drugs flow through the body into, say, different organs. These might correspond to different organs or tissues here, and the rates of absorption and transfer between these different organs could be given by these rates K1 through K6. So you can encode this type of model first in a directed graph and then in matrix form. So for a directed graph, it's going to look very similar to what we had here in the diagram on the left. We're just going to change those boxes into our vertices. So we have CP, C1, C2, C3. I'm going to draw them in the same orientation that we have here, but there's nothing special about this orientation. I could move around and put these vertices wherever I want on the page. What's important is the edges between them and the weights that go along those edges. So from CP to C1, we have K1. From C1 to CP, we have K2. C1 to C2, K3. C2 to C1, K4. C1 to C3 is at K6. And C3 to C1 is at K5. As before, we can encode this information in a matrix. So I'm just going to give an indication on each of these columns and rows as to what they correspond to. Ordinarily, you wouldn't write these things in, these labels that I'm putting here, which I'll highlight. These are here just to help clarify what's going on. Okay, so we can see in this model there are no loops. So because there are no loops, this main diagonal here is going to be 0. So there's nothing going from a compartment to itself. Then let's work down this first column here, thinking about everything that flows out of CP. So what flows out of CP? We just have this K1 here, going from CP to C1. No other arrows, so those are zeros. C1, there's quite a lot going on for C1. So we have this arrow here going to K3, and we also have this arrow here going to C3 at rate K6. So we need to link up our, oh, I've nearly forgotten one then. We also have this one here. So C1 to CP goes at rate K2, C1 to C2 is at rate K3, and C1 to C3 is at rate K6. Okay, the next C2, we just have this one arrow here going to C1 at rate K4. And everything else is going to be zeros. And then C3 has this arrow here going at rate K5. Realize that I've put them in the wrong row. This should have been a 0, and this should have been a 0. This should have been my K4. It's a K5, and this is a 0. Okay. So, like I said, we can go back and forth between these graphs and these matrices representing movement between them in a compartment model. Okay, so if you recall earlier in the semester, we went through an example of a compartment model when we first introduced our matrices, looking at an example of car sharing service at the Burnaby and Surrey campuses for SFU. So here we are told that every day 2/3 of the cars borrowed in Burnaby are returned to Burnaby, 1/3 to Surrey. Similarly in Surrey, 2/3 are returned to Burnaby and 1/3 to Surrey. So we can use a compartment model to describe this, and we can represent it as a digraph. So how do we encode this information? Well, we're told that B here for Burnaby, S for Surrey. We have 2/3 of the cars that start in Burnaby go back to Burnaby. So there is a loop going from B to B, and it has weight 2/3. We have 1/3 of the cars that start in Surrey get returned to Surrey. So we have a weight of 1/3 here. And then 1/3 of the cars that start off in Burnaby go to Surrey. And then 2/3 of the cars that start in Surrey go to Burnaby. So that's our digraph. And then you can represent this in matrix form by just converting that information into a matrix. So the loop from B to B has weight 2/3. The arrow from B to S has weight 1/3. From S to B has weight 2/3. And from S to S has weight 1/3. Okay, one last example here just to make sure this is clear. So we've met these types of models before where we have different age categories. Here we've got juveniles, sub-adults, and adults. And then we're told some information about each of these populations. So when they're dying and how they're maturing and the types of offspring that are produced. So we want to, again, put this word problem into a digraph and into a matrix. So what does that look like? I'm going to call my vertices J, S, and A for my digraph, juveniles, sub-adults, and adults. And let's work through each of these things. In fact, I'm going to do my digraph and my matrix at the same time. J, S, and A here. J, S, and A. Okay, so first of all, we're told that, let's see, 11% of juveniles die and 25% of juveniles mature into sub-adults each year or each generation. So that means that 25% of my juveniles maturing into sub-adults means there must be an arrow here of weight 0.25. If 25% die and 11% mature, start off with 100%, be minus 25, be minus 11. So we're going to be subtracting 36. So that means that 64% of my juveniles must stay as juveniles. So we have a 0.64 in the J to J loop, and in the J to S entry, which is going to be here, we have 0.25. And there is no movement from J to A. Okay, next line. So next line, we're told that 9% of sub-adults die. They produce on average 0.11 offspring, and 20% of them mature into adults. So let's encode, first of all, let's do the aging first of all. So we're going to have S going to A. 20% of them, so 0.2, go from S to A. So that means in our S to A entry, which is this one down here, you're at 0.2. We are told that they produce 0.11 offspring. So S to J is going to be 0.11. And then we need to calculate those individuals who are staying in this category here. So we have 9% are dying. So we start off with 100%. We lose 20% through aging, and then we lose 9% through mortality. So we lose 29%. I should write these as, can't remember what I wrote previously. I might have written this is mixed up my percentages and my proportions. I'm going to do this as percentages here. Apologies if I did mix that up before. So you do 100 minus 20 minus 9 for our percentage that is going to be staying as sub-adults, which is 71%. So that would be 71%, or a proportion of 0.71 stay as sub-adults. So we have 0.71 here. And then lastly, we're told that 33% of the adults die, and adults produce on average 2 offspring. So we're going to have an arrow going from A to J, 2. That goes up in here. There's no de-aging, so adults don't go into sub-adults. This is entry 0 here. There's no arrow going from A to S. And then we need to account for those adults that die. So 33% die. So we do 100 minus 33, which gives us 67. So 67%, or a proportion of 0.67, stay as adults. That's this entry here. Okay, so have a go at practicing going back and forth between digraphs and matrices. And we'll talk a little bit next time about how we can use these representations of digraphs and compartment models to understand Markov chains and page ranking algorithms. Okay, thanks very much.